So we're continuing our discussion of matrices. This is the third video in section 4.1. And we want to go over some definitions. So first of all, let's define a square matrix. So far, the only matrices that we've seen have been square matrices. And no surprise, what a square matrix is one matrix that has the same number of rows as it does columns. So a 2x2 matrix, 3x3, 4x4, etc. These are all square matrices because they are actually square when you write them down. Okay. Square matrices are nice because they have nice properties. Another matrix which is important is a n by 1. So n is the number of rows, so it can have however many rows, but it can only have one column, and that's called a column matrix, or what's a very common word is a vector. So a column matrix is one that looks like this. So it's just one column and then your numbers here. Okay. So that's a vector or a column matrix. Third definition, the n by n, so it's square, has to be square, identity matrix. I is 1 for every element, I11, I22, that's the and so on and so forth, and the diagonal from the upper left to the lower right, and 0 everywhere else. So that one is best described by actually looking at some. So the 2x2 identity matrix is this. 1 on the main, this is called the main diagonal. 1 on the main diagonal, 0 elsewhere. The 3x3 would be 1 0 0 0 1 0 0 0 1. So that's the 3x3 identity. 4x4 would be 1 1 1 1 0 0 0. So I cannot screw this up. 0 0 1 0 0 0 0 1. Okay. So on and so forth. So these are important, and you might have a glimmer of why because of the name of them. So if you remember what an identity is in math, like the arithmetic identity or the multiplicative identity, let me just remind you. The multiplicative identity for real numbers, we all know it. It's the number that when I multiply this, say a is some value, what number can I multiply it by and it remain unchanged? Well, that's 1, right? So 1 is the multiplicative identity. The arithmetic identity, what is that? Well, that's when you add something to a number and it remains unchanged. And we all know that one too. It's 0. So 0 is the arithmetic identity. Okay, so that should give you an idea of what the matrix identity is. So the matrix identity I, it is the multiplicative identity for matrices. So in other words, it's the matrix. If I take some matrix A and I multiply it by the right size matrix I, then I just get the original matrix back. And the nice thing about the multiplicative identity is it's actually commutative, so I can actually do this in the other order and it doesn't change anything. Okay, now we'll see that, but one way you can see this is by actually doing the multiplication, but that's what the identity matrix is all about. So you can actually call up the identity in your calculator using these commands. So we'd go to the home screen, I'll just do it, and we turn the calculator on, second matrix, and if you go to math, we hardly ever use this menu, but if you go to identity, whoops, and then you put in the size of the identity. Let's say I want to look at the 3 by 3 identity. It will just pull it up for me. So there you go. Okay, and so this slide here is talking about the arithmetic, or sorry, the multiplicative identity thing that I was just discussing. Multiplying a matrix by its identity leaves the matrix unchanged. Okay, so continuing along with our definitions, before we kind of wade into all this, let me just get to what it is that we are defining. We are wanting to define something called the inverse matrix. And what the inverse matrix is it's, if I have some matrix A, if I can find another matrix B such that when I multiply these two matrices, I get the identity, then I have the inverse matrix. So basically, so you have to have a matrix to begin with, and then the inverse matrix of A is some other matrix that kind of turns it into the identity when we multiply. So a few more details about this. We've got our initial matrix has got to be square. All right. So it has to be a square matrix. We're not going to talk about identities for non-square matrices. The other identity, or the inverse matrix, will also be square, and it has to meet this condition that when I multiply A times B or B times A, I get the n by n identity. If all that happens, then this matrix B is actually the inverse matrix, and we won't call it B, we'll actually call it A with a little inverse -1 written up there. So A -1. So this is analogous to having say, if I want to multiply, say, the number 3 times something and get 1, what do we multiply it by? Well, hopefully you know that I multiply it by 1/3, and 1/3 is the multiplicative inverse of 3. Okay. Now it's pretty easy to compute the multiplicative inverse of a real number, but how do you compute the inverse of a matrix? Well, that's kind of hard, actually. You have to use some linear algebra, which is what we're doing now. But we're gonna let the calculator do this. So to find an inverse, use the calculator, and I'll show you how in just a minute. But another point that we need to discuss is this last statement right here, is that not every square matrix even has an inverse. So that's kind of different than the real number situation. Like, every real number has a multiplicative inverse except for 0, right? I mean, you can't compute 1 over 0. So real numbers are a bit different, but matrices have some conditions. Now there is a way to test a matrix to see whether or not it has an inverse, but for our purposes, what we're just going to do is this. If the calculator if it gives you an error, and I believe it says a singular error, then your matrix doesn't have an inverse. Okay, so I guess it's important now that we actually learn how to find the inverse in the calculator. So let's talk about that. So here's an example, and I'll just do this on screen here. So we're going to do the matrix 2, 4, 3, 1. I think that's still my matrix A. Let me check. Yeah, it still is. Okay, so I want to find the inverse of matrix A. So here's what we do. It's very easy. You see this button right here? Inverse. You just call up the matrix A. Actually, let me do that whole thing again. I go to matrix, call up the matrix I'm interested in, hit this button, the inverse button, and that's it. Then we just hit enter, and that is the inverse matrix. So the inverse matrix is right here, minus -0.1, 0.4, 0.3, and -0.2. So what should happen then when I multiply matrix A times matrix A's inverse is I should get the identity, and I do. All right. Okay, so it's time to get back to actually talking about linear equations and what the point of all this matrix stuff is. So as you might have suspected, we are going to use matrices to solve linear systems. And here's the method kind of in a nutshell. Now this is going to be explained for a 2x2 system, but we're going to easily expand this to talking about other size systems pretty soon, but let's start with a 2x2. So if I have some system of 2x2, two equations and two unknowns, ax plus by equals p and cx plus dy equals q, we're going to define three matrices. Matrix number one is going to be the coefficient matrix. And I guess maybe before we get into this, talking about the matrices, let me say one very important thing. You have to put your system into this form. So if it's written in like y equals mx plus b form for both of them, that does not work for matrix methods. I have to get it in this form. So this form meaning normal form for each matrix. So the constant has to be over here on the right hand side, and the variables have to be on the left-hand side, and they must be in order. So if I have x first here, then x must be first down here. And that's got to be consistent throughout the entire system, all right? So you can't have x, y, and then y, x. Otherwise, your answer is just going to be wrong, because position is very important with matrices. Okay, so back to the example. So let's say that you have some 2x2 system, and you organize it, you move everything around so that it looks like this, and now we can form these matrices. As I was saying, the first matrix is the coefficient matrix. The coefficient matrix is just the 2x2 matrix that we get by pulling these coefficients, A, B, C, D, and that's what you see down here, A, B, C, D. Okay, that's the first matrix. So these are actually numbers. The next matrix is the matrix of unknowns, and we give it this title capital X, and it's just got it's a column matrix or a vector, and it has just the unknown variables in it. So in this case it's going to be X and then Y, and it's in the same order down as these are from left to right. And then finally we have another vector, another column matrix of constants that is pulled from the right hand side. So you should have nothing in here but these constant values that you get from the right hand side. And if one of these is 0, then you put 0 in for the entry. Okay, and so those are your three matrices. And what we can do is now rewrite our linear 2x2 system in a matrix equation form right here. Now you might wonder, how does this work? Well, why is A times X equal B in matrix form the same thing as this little 2x2 system? Well, it all goes back to matrix multiplication. If you multiply this matrix A times this column matrix X, you'll get row 1 will be A times X plus B times Y, which is the matrix definition of multiplication. And row 2 will be C times X plus D times Y. And that's the second equation. So that will give you your matrix, your 2x2 system. Now finally, the last step here is that to solve the matrix, we can multiply by both sides by the matrix inverse. So I multiply this side times A inverse and this side times A inverse. And when I do that, over here, those cancel, and that gives me the identity. And over here I have A inverse. And so that's actually my answer. I'm about to run out of time on this video, so we'll have to finish this one in the next one. But that's it in a nutshell, and then we'll flesh this out in just a moment.